Hi guys. So I'm gonna continue with Gerbes. I need to make some preparations. So let me start. So let's say this is gonna be on inner and outer automorphisms. Automorphisms and isomorphisms and groupoids. Okay, so recall that a groupoid is just a category with one object, or sorry, I always want to say category with one object for groupoid. It's a category where all the morphisms are invertible. Okay, so a connected groupoid, so let's say G is a groupoid, is connected if for all, let's say, G1, G2 in G, so every two objects of G, the Hom set from G1 to G2 is not empty. Okay, so this means that we can find maps for each of them. Okay, so let me give you a definition. Okay, so let's let gamma be a group. So recall that an inner automorphism is just a map, an automorphism, where we take X and we map it to X, let's say, well, it could be like this, X to the Y, Y inverse XY, where Y is an element of gamma. So this is a operation by conjugation. So an automorphism coming from conjugation. Okay, so so let gamma 1 and gamma 2 be groups. So an outer isomorphism so here well we want it to be not an inner isomorphism. Okay, so what you can do is you can take so in the category of groups you can look at here gamma 1 to gamma 2, and then you can mod out by the inner isomorphisms of gamma 2. Okay, so here, so let's look at the action here. So here's the action by conjugation here, and what you can do is you can take one of these guys. So suppose I have, let's say, phi from gamma 1 to gamma 2, and let's suppose I have let's say, I don't know how we want to call this, sigma y. Okay, so this is from gamma 2 to gamma 2. Y is in gamma 2. And this is the operation here. So this is going to be defined sigma y of x. Okay, so this is from this. So then the action, so this guy here, this is an element of the inners of gamma 2. This is maybe I should say not just group, sorry, this is iso, okay? I mean, I guess we could do it for just group homomorphisms, and that would just be an outer morphism, but I guess, well, okay, we'll do this. We'll stick with isomorphism, okay? So, so we do this, and then there's an action, so the action of, so this, I guess this is a right action, goes to sigma y composed with phi. So this is the right action of this inner part on these isomorphisms, or if you wanted to do it just group homomorphisms. Okay, so this is an outer isomorphism, not just group homomorphisms. Okay, so that's that. Okay, so now we have this terminology, and now I can talk about what I want to talk about. Okay, So let's take like a lemma. Okay, so let G be a connected groupoid. Okay, and let G1, G2 be elements of G, and okay, let gamma 1 be the automorphisms of G1, and gamma 2 the automorphisms of G2. Okay, so so 1 is that gamma 1 and gamma 2 are isomorphic as groups. So the automorphisms of one object are the same as the automorphisms of the other object. Okay. The second thing is that so the HOMs from one object to another object are first, there are two things. So they're left torsor under gamma 2, and they're right torsor under gamma 1. Okay, so we could proceed in a couple ways. Okay, so let's just prove these, proof idea. Okay, so this is really elementary. So here, so since it's connected, right, so there exists some F from G1 to G2, so this is not empty, right? And then, so then what can we do? So I'm going to define a map from gamma 2 to gamma 1. So gamma 2, or let's say gamma 1 to gamma 2. Okay, so what you could do, so let's take this. Okay, so gamma 2 acts like this. So we have a sigma and it acts here. Okay, so what you could do is, so we're going to do gamma 2 to gamma 1. Okay, so what you do is you take G, you go to F, you apply this, and you come back. Okay, so here you take sigma, and then you map it to, well, okay, so you go F composed with sigma composed with F inverse. Okay, and so that you can check that this is a group isomorphism. Okay. Okay. Okay, so this gives you this, but this depends on a choice. Okay, so the idea is that this depends on a choice here. Okay, so then another thing is how to get the left torsor and right torsor. Okay, so the left torsor and right torsor structure. This is really easy. So again, so suppose we have one of these guys. So the left action, okay, here, so F, so sigma 2, so this goes to, well, this is just silly, so this is the left action. And then the right action, so suppose you had, so F comma, okay? So suppose we had a sigma 1 over here, so the right action is just as stupid. Okay, so this is a right action. Okay, and then you check that the action is full and faithful. Okay. Okay, so that they orbits the whole thing, and that if two guys go to the same guy under the action of an element, then they're the same. Okay. So we have this non-canonical isomorphism here. So the reason I started talking about outer automorphisms is because we're going to make this canonical. Okay, so lemma. So here, so the G connected groupoid. And let's take F, okay, let's take G1, G2, objects of G. And let's take f in a hom from G1 to G2, so something like this, okay? And let's take G in here, okay? And let's define, okay, so let's look at a certain map, okay? And so what we're going to do is we're going to, so we had this isomorphism of groups from gamma 1 to gamma 2. And so what we can do is we can look at, so let's take, okay, so let's look at this map again. So G1, G2, I always forget how to, this is F. Okay, and suppose we have sigma here. Okay, so sigma here. Okay, so what we could do is we could go to F, we go to sigma, then we go back with F inverse. Okay, so we have, G2 goes to, so I'm not done stating the thing. I just have to remember how this works every time. Okay, so here we have sigma, it goes into here, sigma F, F inverse like this, okay? And so this thing defines an isomorphism, so this is what we call the gamma 1, and this is what we call the gamma 2, okay? So given an F, so this is kind of like a construction here. Okay, and so we had given an F, so F, so G, G1, G2. Okay, so this goes to an automorphism of, an isomorphism of from gamma 2 to gamma 1. Okay? Okay, so there's a construction, maybe we can call this phi of f. Okay, so this is the automorphisms of here to the automorphisms of here. Okay, so we have this construction, okay, that I want to talk about. Okay, so now I'm going to talk about the lemma. Okay, given this and this, then phi of G1 is congruent to phi of G2, or phi of f, sorry. Phi of G is congruent to phi of f as outer isomorphisms. Okay, so that they're the same under conjugation. Okay, and okay, so proof of this is really easy. So we just look at the definition. So so phi f of sigma. Okay, maybe I should have started this over here. So phi f of sigma. So this is F inverse composed with sigma composed with F. Compose. Okay, and so here what we could do is we could do F inverse composed with G inverse composed with G here, and then inverse composed with sigma composed with G composed with G inverse composed with F. Okay, so here, what do we have? Here, this part is so what do we have? We have F inverse composed with G, okay, composed with here. Now this comes from the torso structure, so this is phi of G, okay, and then this is G inverse composed with F, okay. And so here, let's look at what this does. So here we have G1 to G2, okay, and we had F, and then we had G as well, G, okay? So we're going G, and then we go G, this inverse, so here to here, okay? So it turns out that F inverse composed with G is an element of the automorphisms of G1, okay? And this is gamma 1, okay? And let's call this thing sigma, okay? So if that's sigma, then this thing here is sigma composed with phi of G. Oh crap! Maybe I shouldn't have called this sigma. Let's call this alpha. I mean, because I just don't want to call it sigma because I don't want it to be confused with the action that I had before. Okay, so this is alpha here, composed with alpha inverse. Okay, so here, and then this looks like. So did I want to do it this way? This is a right action. Okay, so yeah, so this is okay. This is fine, right? So this here is an action by conjugation. Okay, so these are the same as outer automorphisms. Okay, and that's all I wanted to say about that. Okay. Hi guys, I stopped the video prematurely. I need to say a little bit more. I realize I need to talk about outer isomorphisms of sheaves. So outer isomorphisms of sheaves now. Okay, so what we're going to do is we're going to take so let K and L be sheaves of groups on a site X. On a site, oh sorry, I said X, let's say S, okay, with the topology T, okay. Let's say that, so let's say locally, we think of having lots of maps between K and L, or isomorphisms K to L, i.e. For U and S, right, we're going to have things like maps like this. Okay, so like this. So like this is this happens, for example, for vector bundles, right? So vector bundles look like, or locally free sheaves, looks like some copy of the structure sheaf. Okay, so this is a situation that appears. So okay, so then so what we can do is we can take these guys and we can define. So maybe this is more of a definition than a notation. We can define this here. Okay, so this is a sheaf here. This is a sheaf on S, or a pre-sheaf. Okay, so I guess, let's see, is it a sheaf or a pre-sheaf? So if these are sheaves, then I think this is a sheaf, but let's say pre-sheaf to be safe right now. Okay, so we have this, and then so what we can do is there's an action, as we saw. There's an action. So what does this thing do, by the way? We stick in a U. This is just isomorphisms of the restriction as sheaves of groups. Okay, so so we have this guy. So then so we can, there's a definition of an action. Okay, so L is going to act on this guy via inner automorphisms. Morphisms of L. Okay, so this makes sense. And then, so then we can define, so there's a pre-sheaf. Let's maybe call this in L. Okay, so this guy here, this is a sheaf. Okay, so this is the image of this action is in L. Okay, so then let's make a definition here. So then we're going to define this pre-sheaf. So we get associated to this is a pre-sheaf of isom L modulo in L. So this is a pre-sheaf so this is a presheaf on S of groups. Okay, and then we take the sheaf associated to the presheaf, is the sheaf of outer automorphisms. So this is going to be out KL, and this is the sheaf of outer isomorphisms. If I said automorphisms, I'm sorry. This is a sheaf of outer isomorphisms. Okay, so that's what we have. Okay? All right. Okay, and so just a quick thing. What do these elements look like of out look like? Okay. So I'm going to answer this question. So the answer is that we're going to have, so we're going to give a collection. So elements. So this is a question. This is an answer to the question. Elements of out KL U, let's say for U and S, are given by the following data. Let's say equivalence classes of the following data. Okay, so first we pick a cover, U from UI to U, okay, UI to U, I and I. So this is the site here that we're giving on S. So this is in tau of U. Okay, so this is a cover. Okay, and then so then what we're given is a collection of so let's say psi. So these guys. So we're given a collection of phi's. Okay, so here I and I. So we're given this. So where phi are isomorphisms from UI. Let's say. So we're doing K restricted to UI to L restricted to UI, such that such that, and then now we're going to have another condition, okay, such that, okay, for each one of these guys, okay, so for all Uij, so, and then again this is UI crossover Uj. We have, so there exists, so there exists some, so what do we need to say? So there exists a cover, okay, Uij, so this is a curly Uij. And so this is from Uijk now to Uij, and K varies over an index set that depends on I and J, and this is a cover of Uij, such that, and there exists this guy, and there exists some let's call them lambda ij's, lambda ij. K's in L of Uij, such that, okay, such that, all right, now we compare phi restricted to Uij is equal to an outer automorphism, so we'll do this. So this is the action by conjugation. By conjugation. Okay. Of phi j restricted to uij. K, sorry, K's here too. Okay, so, all right. So now we're going to do, this is like the Gerbes, this is kind of Gerbes, okay? So what we have here is, so the question is, what do these outer automorphisms look like when we actually do it for sheaves? Okay, so what are we going to have to do? Okay, so here, this thing, when we originally did it, it wasn't necessarily, so when we defined it here, when you just define it naively, this isn't necessarily a sheaf, okay? We're also assuming that locally we have maps here from isomorphisms like this. Okay, we have these, maybe these things can be thought of as like trivializations. Okay, so this guy's not necessarily a sheaf, so we're doing the sheaf associated to the pre-sheaf, okay? And so to do that, I need to artificially glue things together, okay? And to artificially glue things together, we're just going to actually make the sheaf condition that H0 is defined by things on open sets, right? Sufficiently small open sets where things agree, okay? And so that's what this is saying. This is saying that here, to define a section of here, we're going to make this artificial gluing condition, right? And by artificial gluing, we mean that these guys here, they're going to define isomorphisms here on these guys, okay? But we need them to patch, and to get them to patch, this means that on UI and J, they are going to patch even if once we restrict them a little bit further. And here, this is the patching condition. This says that they agree as outer automorphisms, and this is the inner automorphism that they, or outer isomorphisms, and this is the inner isomorphism that they, or inner automorphism that they differ by. Oof. Okay, so I'm not going to explain any more of this, but I just wanted to say this because this is going to appear in this construction of bands for Gerbes.